Welcome to our service training program on the theory of power shift transmissions and torque converters. Now for a short lesson in the theory of power shift transmissions. You'll find our power shift transmissions in a variety of machines like tractor shovels, dozers and scrapers, cranes, graders, forestry equipment, off-highway trucks, and underground mining loaders and trucks. We're going to look at just how a power shift transmission works, but first let's ask a more basic question. Why do you need a transmission at all? Well, it's because the engine by itself just won't do the job. The work we do with these machines requires high speeds and low speeds, but enough torque at any speed. The problem is that an engine really only puts out within a certain RPM range. Run it slower than that range and it just doesn't have the power. So we use a transmission to keep the engine at the proper RPM while we're doing work that otherwise would be too slow or too fast for the engine. The transmission gives us the flexibility to do a variety of work, even though the engine doesn't care for a variety of speeds. So what is a transmission? It's a set of gears and shafts which transmit energy from the engine to the driving wheels of a machine. And this transmission gives you three big pluses. The machine doesn't always have to be rolling while the engine is running. You put that transmission in neutral and the engine can turn over even though the machine is standing still. When you need a lot of power and a lot of torque, like for going up a steep grade or pushing something heavy, shift to low gear. When you need speed, shift to high gear. A power shift transmission is a little like an automatic transmission in that the gears are constantly meshed and the power comes from a torque converter. Instead of clutch bands, a power shift transmission has clutch discs which engage the gears. These hydraulically operated clutches are not activated by some sort of mechanical governor, but are activated by the operator himself. If you understand these hydraulic disc clutches, then you'll have a pretty good understanding of the power shift transmission in general. Imagine a shaft with grooves cut in its surface and a disc with tongues that fit the grooves. As you can see, a disc like this could slide back and forth in the grooves, but could not rotate independently of the shaft. Now imagine a cylinder with grooves cut in its inside surface and a disc with tongues to slide in these grooves. Once again, the disc can slide back and forth, but because of the tongue and grooves, the disc cannot rotate independently of the cylinder. Now, if you were to take the grooved shaft and place it within the grooved cylinder and alternate discs so that one disc is tongued to the cylinder while the adjacent one is tongued to the shaft, you would have the beginnings of a clutch. All of the discs in this mechanism can slide back and forth, but some discs turn only with the cylinder while others turn only with the shaft. If a piston is installed at one end and a path is provided for high-pressure oil, then the mechanism is completed. Imagine that the cylinder is turning and the shaft is not. If the oil forces the piston against the discs compress together, forming a friction sandwich. The cylinder's discs pressing against the disc on the shaft cause the whole mechanism to turn as one unit, and that's how the hydraulic clutch works. We have refined this basic mechanism, and you should understand some of these refinements. But before you can understand the refinements, you'll need to know a few basic principles of hydraulics. Here are two pistons in an oil-filled cylinder. If you press down on one piston, the oil transmits the pressure to all interior surfaces, but the only surface that gives in to that pressure is the bottom of the other piston, piston B. Now, if both pistons are the same size when you press down on piston A, piston B will rise out of the cylinder just as fast as A is depressed with just as much force. Here's where it gets interesting. If piston B is smaller than piston A, when you press down on A, the smaller piston will rise out of the cylinder faster than the larger piston is depressed, but with less force. You're trading force for greater speed. If the bottom surface of piston B is greater than piston A, when A is depressed, the larger piston will rise out of its cylinder more slowly than A is depressed, but with more force. Here you're getting more force, but giving up speed. You can see that the amount of piston surface determines how fast the piston moves and with how much force. Now you're ready to understand the step piston. The piston within the clutch has two surfaces. When the oil is directed to the piston, it initially acts only on the step piston's small surface. The piston moves rapidly toward the discs, but without maximum force. As the discs squeeze together, causing resistance to piston movement, The oil is forced around the edges of the small piston surface and begins to act on the larger surface, providing very great force. You will find that some clutches use a step-up piston and some use a step-down piston. Either way, the same principles are involved. The greater the surface, the greater the force. So our patented step piston design functions with clutch disc resistance to provide quick, smooth, and powerful application of force. So far, we've only talked about applying the clutch. Let's look at how the clutch is released. First, you've got to release the oil pressure from behind the piston. This permits the piston return springs, which have been compressed by the moving piston, to push the piston away from the discs. But releasing oil pressure doesn't do the whole job. Some of the oil can escape back through the inlet passage, but because the drum is spinning rapidly, the oil flows with centrifugal force toward the outside of the drum, making escape through the central inlet passage difficult. But as centrifugal force causes the problem, then centrifugal force can solve the problem. This is a check ball fitted in a ramp at the outer edge of the drum. The ball rolls up the ramp because of centrifugal force, revealing an escape passage for the oil. This ball permits a quick release of the clutch. When the clutch is reapplied, the high pressure of the oil forces the check ball into the neck of the escape passage, preventing a loss of pressure. So now you know about a couple of refinements we've engineered into the hydraulic clutch of a power shift transmission, the step piston and the ball check valve. But up till now, you've been looking at a very simplified diagram of the clutch. This gives you a better idea of what the real thing looks like in some models. Here is the step piston, the small and large surfaces, the discs, the piston return springs, the inlet passage, and the check ball escape passage. Here is a review of how the oil activates the clutch. High pressure oil is sent through the oil inlet passage, forcing the piston into the discs and compressing the piston return springs. When the pressure is released, oil escapes back out the inlet passage, but also through the centrifugally operated check ball valve. A power shift transmission is nothing more than a series of these clutches which lock gears and shafts together to select various gear ratios or neutral. A power shift transmission has one clutch for each of its speeds, plus one clutch for forward direction and another for reverse. So this 3-speed transmission has a total of 5 clutches. Anytime the vehicle is moving, 2 of the clutches will be engaged, either the forward or reverse clutch and one of the 3 speed clutches. These clutches are activated through a device called the transmission control valve, which you will find mounted on the transmission case. This control valve does 2 things. It controls the amount of oil pressure to the clutches, and it permits or prevents oil flow to the various clutches, kind of like a traffic cop sending oil down one path and stopping it from traveling down another path. Now let's talk about how the valve regulates pressure. Oil is pumped into the valve here by a gear-type pump, sometimes called the converter charge pump. But the clutches operate best only within a limited pressure range. Here's what does the job. It's called the pressure regulator spool and consists of a cylindrical spool which is fitted into a smooth bore. The bore has a port for oil. As pressure builds, the spool is forced against its spring and the oil port in the bore is exposed, and the oil can travel on to be distributed to the designated clutches. If too much pressure builds up, the spool compresses its spring still further until a second port is exposed. This second port bleeds off excess pressure, sending oil to the torque converter. So that's how pressure is controlled. Very similar devices are used to activate the various clutches. After oil passes the oil regulator spool, it flows to the forward-reverse spool. When the spool is in this position, the forward clutch is activated. In this position, the reverse clutch is activated. This position gives you neutral. Right next door is the position which gives you first, second, third, or fourth. And because the forward-reverse spool is independent of the speed selection spool, you can have any of these speeds in reverse as well as in forward mode. So you can see that there are basically 3 spools involved in the transmission control valve. First, the spool that regulates pressure, then the one that gives you forward or reverse, and finally the one that gives you speed selection. You'll find more detailed power flow diagrams for each power shift transmission in its shop manual. Well, that's about it. A power shift transmission is nothing more than a series of clutches which lock gears and shafts together to select various gear ratios and forward or reverse mode. This selection is accomplished through the transmission control valve, which sends oil at the proper pressure to clutches selected by the operator.